All right, thank you. So first, I want to tell you about my overarching goal, really. So there are multiple ways to define type conversion in a type theory. The first one is usually the one that type theorists use. I'm going to call the specification. So it's very idealized. It has reflexivity, transitivity rules, all and good. But in the end, we want to have proof assistance that actually work. And so we did an algorithm to implement this. And of course, since we have two definitions, we want both of them to be related to be sure that all is good and well. But first, there's already an issue with what I will consider as an algorithm, because first, usually algorithms take the two terms they want to compare and put them in normal form, which is something that is very difficult to assume. The fact that all terms have a normal form, or at least a head normal form, is something that's hard to prove when it's provable, and it's also not even true in all cases. Also, algorithms can do some fancy stuff. They don't always compare heads. They can have shortcuts when, for instance, both terms are syntactically the same. So this just means that there are whole classes of what algorithms can do, and I want to abstract over this. So this is what I'm going to define as the new algorithm. So what this can do is just take the two terms, do head reduction on them as many steps as it can do, or stop at any time, and at any moment take the two terms, compare, and if they have the same head constructor, do recursively the test on all subterms. This should encompass what all algorithms can do, and let's see how these two notions relate. So to prove that the algorithm is correct is actually not too difficult, because all of the rules that an algorithm can do have an equivalent in the specification. So I can tell you that this is quite easy to prove. And on the other hand, most of what happens in a specification can be proved to happen in an algorithm. Either you have directly the same rules, or you can do a simple induction, for instance, for reflexivity and symmetry. So there is really one outlier, which is transitivity, and it's much harder to prove. So how do we try to prove transitivity? Well, first, let's see why a simple induction doesn't just work. And for this, I will need to go in a bit of details. So what happens if the algorithm, so we start with two derivations. On the one hand, we do a beta reduction, and on the other hand, we only use congruence rules. So we get to this kind of state, and for us to resume the induction, we need to take those syntactic beta redexes for 0 and 1, do the reduction, and resume with T0 substituted with U0 and T1 substituted with E1, which is true. We can do this because algorithmic conversion is substitutive, but this substitution does not preserve the sizes. So the induction cannot go through, and this is just a dead path. So now there are two actual ways to prove transitivity. The first one is to go through logical relations and deterministic reduction. So what I was telling at the start, you take the terms, you do head normalize them. And when you reach head normal forms, the transitivity is much easier to prove because it's basically only congruence rules. But in exchange for this, reflexivity is now much harder to prove because you need to prove that all terms normalize. And this is not something that I want to assume because I want to have a theory in which it's either too hard to prove or not even true. So this leaves me with one other path. It's the same path that is used for regular lambda calculus, untyped lambda calculus, is to define parallel relations, and also the Hindley-Rosen technique, because I'm going to have more than one relation. And so for this, I'm going to introduce a middleman between the specification and the algorithm called joinability, and prove that joinability first is transitive, and hopefully the other required properties will be easier to prove. But for now, I'm focusing on transitivity or joinability. So first, let me define what I mean with joinability. So first, we take the specification for the type conversion, and we split it between different relations. So we are going to have parallel reduction, eta parallel reduction, and alpha equivalent. All of these, by virtue of them being parallel, will have congruence rules, type conversion, And also to note type conversion, the most simple is to just instantiate it with the relation we're defining because it is a conversion. But for now, I'm just going to leave it abstract and see what the constraints on this conversion are going to be in the following proof to see only at the end whether we can instantiate it with itself or sometime, or maybe with another definition. And so what makes each of these relations different? The base blocks. So parallel reduction has beta as a base block. Eta reduction has eta expansion as a base block. It's a bit counterintuitive, but eta expansion is better behaved. Also, not included in this slide, I will have inductive in my theory. Like, for instance, I have pairs with the eta rule. So, and this will play a role a bit later. And so all of this combined, the joinability relation is defined as you take both terms, you do any amount of parallel reduction on them, and at the end, they have to be alpha equivalent. So how do we prove this to be transitive? We start with the diagram you have at the top, so two joinability relations glued one to the other. And what we're trying to do is to swap around the arrows in the middle such that we can rearrange everything to fit in the shape of a single joinability relation. And for this, we are going to need these commutation bricks to treat each kind of commutation. And so a commutation can either be direct, so there's nothing left behind, or in the case of eta versus eta, there can be an alpha equivalence left behind, but it's going to be fine because we're going to prove that alpha equivalence is transitive, and it also commutes with all other arrows. Also, I should just note that when I mean alpha equivalence, it's a bit more than simply alpha equivalence. It's going to have other properties, including the fact that annotations will be equivalent using something stronger. So now that we have a plan, if we only look at the terms part of the commutation, it should be all fine. So I'm really going to focus on what the properties of the type conversion will require, because these are the ones that make the proof much harder. So first, I'm going to talk about something that is not actually a constraint on type conversion, but since we're going to do an induction, so for each of the commutations, we're going to do an induction on one of the derivation, and so we're going to do inversions on the other one. So this means that to have any kind of synchronization of the types between the two derivations, we need either type uniqueness or some form of type principality. Otherwise, we are just lost. And similarly, since we're going to deal with multiple types and we need to swap them around, move around, we are going to need reflexivity and transitivity of type conversion to apply to move the types around. And also, since we have annotation in our terms, and we are going to do reduction on all sometimes, so including annotations, this means that type can reduce, and we need to account for that. And this translates to the fact that all of our relations, parallel reduction, eta reduction, will need to be included in conversion. So that's for the easy constraints. Now we're going to jump a bit higher and a bit more in the gruesome details. This is the case of what happens when you have a beta reduction on the one hand and congruent rules on the other hand. So it's similar to the case I was alluding to before. But here, since it's parallel reduction, it works much better. To note, so by induction, we can find the TF and UF. So the only thing to really see in this slide is the fact that we need this subst. So the fact that parallel reduction is substitutive for this commutation to work. But parallel reduction itself was constructed. This whole point is to be substitutive as opposed to other definitions of reduction. That's all and well, but the type conversion in parallel reduction will itself also need to be substitutive. So let's just add this to the list of requirements. And now let's go to the most tricky part. What happens when you have an eta expansion against a beta reduction? So first you have to know that in a beta redax. So let's take the lambda xt applied to U. Lambda xt itself is a lambda, so it has a pi type, but also it's applied to U, so it has another pi type. And for us to, and those two pi types are convertible because it's the same term. But if we want to actually reduce the beta redax, we need to do a substitution. So we need the fact that A and A prime, the domains are convertible, B and B prime, the codomains themselves are also convertible. So this means that at least for this equality conversion of pi types, this needs to be injective. Now, the thing that happens when we have an eta expansion is that here on the right, we are introducing a new beta redax, lambda xt2 applied to y, ex nihilo. So it has to be inside of a beta redax, but this beta redax is a new one. So this means that if we had any hope of including the requirement of injectivity inside the requirement for beta redax to happen, it is a bit dashed because we can create new redexes anywhere. So we need the fact that the injectivity of type conversion, we can't just have it locally, we need to have it globally. So we can add this. And this is what happens in the other case of eta expansion. It's a bit similar. If we do an eta expansion, but this time for pairs, we're ending up with something which is just weird and shouldn't exist. A pair applied to something that is not well typed. And that's the argument that we want to actually use. This should not be well typed, and we need to find a way to prove false from this existing. And in terms of type conversion, this translates to the fact that we have a term T which has both a pi type and a pair type, a product type, and we just need to refute this. Okay, so now we have a list. Let's see if we can find candidates to for the type conversion which satisfy all of the requirements. So the first candidate will be the specification, and it will fit for 1, 2, and 3, but 4 and 5, so injectivity and non-confusion, is something that is not easily proved for the specification, since the transitivity rule can just hide everything, and it's not possible. The joinability, so the one I was defining, it has more requirements, so 2, 3, 4, and 5. But again, the issue is transitivity. We were trying to prove it, and we can't use it since we're trying to prove it. Even if we try to do it by induction, it's again not structural, so this just doesn't work. And the algorithm is even worse than the joinability because we're even further from proving transitivity. So all hope is not lost. First, I didn't talk about requirement 0. We can solve it. There are ways to solve it. So either through bidirectional typing or annotations. Both of these make the proof harder to read, harder to work, but not harder to prove. Like, it's not logically harder. It's just more annoying, basically. And also, the list of requirements I made is not actually final. There is some wiggle room. For instance, reflexivity and requirement 2 can be waived if we change transitivity to be stability under reduction. So this just means that there is some wiggle room. It's not absolute. So to conclude, I really want to highlight the fact that when we have a type conversion and it has some eta rules, at least the proof scheme I was showing relies very heavily on the fact that we have a conversion that has injectivity and non-confusion of type constructors. And really, this means that as a whole, if we want to prove adequacy, we need such properties. Transitivity also is obviously required and difficult to sidestep. And I will need more work to find such suitable candidate for type conversion because we need something that's hard to find. Thank you.